In the last segment, we talked about how to recognize redox when we see it. Sometimes we're given half reactions that provide some sort of skeletal, minimalistic sort of snapshot. Other times, we're given a whole, what I'll call a skeletal equation here, recognizing that this is redox and that we have to balance the electrons before we get a balanced skeletal equation. Other times we'll do something that is familiar to us that we've seen before, like single replacement. And when we write a net ionic equation, we can see that we can pull out the half reactions and see that zinc to zinc 2 plus is oxidation, hydrogen to hydrogen gas is reduction. So we're beginning this segment 2 with more examples on how we recognize, for example, single replacement as redox. Calcium is higher on the activity series than hydrogen, so this reaction will go forward. CaSO4 is our product because calcium is a 2 plus, sulfate is a minus 2, hydrogen gas is displaced. Calcium greater than hydrogen. Single replacement. Write a net ionic equation. Okay, so this is total molecular. Total ionic equation is calcium plus, this is an acid, so it will be aqueous. Solubility table will tell us that this is aqueous as well. Hydrogen is a gas, so we leave that alone. Spectators include sulfate, so we have our net ionic equation as calcium, which is a solid, make that obvious, plus 2H plus, yields calcium ion, which, remember, it is aqueous, plus hydrogen gas. What is oxidized? Calcium goes to calcium 2 plus, which means it loses 2 electrons, and therefore calcium is oxidized, and this is the oxidation half reaction. 2H plus 2 electrons will yield H2. 2 electrons here, 2 minuses, 2 pluses equals 0. 2 electrons are involved in the transfer. By now we know that this is the spectators. What is the sum of the stoichiometric coefficients in the balanced equation? 1 calcium, 2 hydrogens, 2 hydrogens, 1 sulfate, which we see up here as well. So the sum is not a mystery. 1 plus 1 plus 1 plus 1 equals 4. Okay? Now, just for illustration, let's also see, by the way, single replacement and redox. Just like on the other page, single replacement, and now we also know that it is redox. Okay, now before we move into oxidation numbers, let's add a little bit here. And so let's come down to the bottom of the page, and let's say that we're going to combine calcium with oxygen. Predict the product. CaO, because calcium is a plus 2 and oxygen is a 2 minus. To balance, 2 here, 2 here. Okay, so we are going to see that this is combination, but we're also going to see that this is redox. Okay? 2 calciums go to 2 calcium plus 2 because we know that calcium 2 plus makes calcium oxide. So we're going to have to put 4 electrons over here. 4 pluses, 4 minuses gives us no charge over here. That tells us then that the calcium is oxidized. we have oxygen gas, 2O2 minus, because it's 2 minus on the oxygen, and there are 2 of them. That means the 4 electrons have to go on the left in order for -4 plus 0 to equal -4, and that's showing us that the oxygen gas has been reduced. So combination is also redox. All right? We're going to see that combustion is also redox, but that's going to come in a later segment. So that is a perfect segue into this question. What do we do when it is not so obvious to identify redox? Well, we have to assign oxidation numbers and then look for a change. Now, depending on what book you have, this is not going to be in your book. Okay, and there should be some ancillaries on Blackboard, including some other videos, some other handouts, lots of practice to help you with this. Because as you move along, particularly if you go into biochemistry, there are multiple ways of recognizing redox when you see it. And so we're going to have to make sure that we figure out all these different ways. Okay, basically it boils down to this. Rule number 1, uncombined elements have an oxidation number of 0. Oxygen is almost always -2, and hydrogen is almost always +1. Rule 3, the sum of the oxidation numbers is equal to the charge and magnitude of whatever it is on your what I'll call species. Then assign oxidation numbers, and then we have to indicate, okay, do we see a change? And based on the change, has oxidation occurred or has reduction occurred? So let's try a few. All right, so let's go back to our calcium plus oxygen yields calcium oxide. Okay, rule number 1 is that calcium here is uncombined, so it gets an oxidation number of 0. Oxygen here is uncombined, so it gets an oxidation number of 0 as well. Our calcium oxide is neutral, but it's also ionic. And we know that calcium has a +2 charge for the ion that went into making it. And we know that oxygen is a -2 because of the ion that went into making it. What we see here is that calcium has gone up. Okay? If the oxidation number goes up, then oxidation has occurred. So in going from 0 to +2, that is showing oxidation. If oxidation numbers go down, then reduction has occurred. So our oxygen goes from 0 to -2, so that is showing reduction. Okay? If I go from, say, ammonia to nitrate, okay? Now the balancing of the hydrogen and oxygen aside, assign oxidation numbers and figure out what has occurred. Well, our rule says that hydrogen gets a +1 unless it's H2, okay? Hydrogen gas is uncombined, so that gets a 0, okay? Rule number 3 says the sum of the oxidation numbers have to add up to the charge and magnitude of whatever it is that you're looking at. So I have 3 hydrogens and each of those has a +1. So our contribution to the oxidation numbers from the hydrogen is +3. The whole thing is neutral. So the number on nitrogen +3 has to equal 0. And therefore the number on nitrogen is -3. This one, on the other hand, has a negative charge. So that means that everything has to add up to -1. Our rule tells us that oxygen is a -2, and there are 3 of them. So that means you have 6 negatives contributed by oxygen. Everything has to add up to -1. So the number on nitrogen -6 has to equal -1, which means that our number here on the nitrogen is a +5. Therefore, the number on nitrogen has gone from -3 to +5. That means it has gone up in a really big way, which shows that the ammonia here has been oxidized. This is showing oxidation. Now remember that oxidation and reduction have to occur together. So you could not put these two together to get a redox. If you have something that's being oxidized, these two, meaning this one. Sorry, I got a little ahead of myself. On this top reaction, you see that this is oxidized, this is reduced. So this is a complete redox. This one is not. I'd have to partner it up with something that is showing reduction. So for example, I could take H+, create H2. The number on the hydrogen here is a +1, in part because it's an ion and it gets a +1, and also it has our rule. This is uncombined. Uncombined gets 0. So our number on the hydrogen here has gone from 1 to 0. The number has gone down, which is showing that our H+ here has been reduced. Therefore, we could pair the two of these to make a complete redox. In the next segment, we're going to look at some more changes. We're going to assign oxidation numbers and then determine if that's showing an oxidation half reaction or a reduction half reaction.